Okay. Hope everyone's doing great. Can someone let me know if you can't hear me? No, just kidding. Let me know if you can hear me. Somebody.
No, you sound really high pitched. And
what?
Really weird.
Oh,
no, I'm just joking with you.
Okay. And then I'm assuming people can see the notes. If you can't see the notes, you can tell me. Awesome. Okay. So the plan for today is basically just more Haskell. And I'm going to talk a little bit about some more functions that we kind of just skimmed over at the end of last Thursday, and then we're going to move into doing kind of a little bit more complicated things. And one is just some examples, kind of using recursion, which I think is one place where functional languages obviously like really shine, and it's nice to be able to use a language like Haskell for recursion, and a lot of stuff that you end up using recursion. And then I don't know if we'll get there, but we're going to talk about either towards the end today or on Thursday pattern matching. Homework 8 is due on Thursday, and then homework 9 is like ready to go, and I'll publish it on Thursday, and it'll basically be more Haskell functions involving recursion and with and without pattern matching. So before I get started, are there any questions that folks have about the homework or just anything? So one thing I'd like, oh, sure. Go ahead, Donovan.
Yeah, regarding the current homework, I think it was the append to the end. I was kind of having an issue with that as to like how to do that. I was looking online and people were saying, like, you have to deconstruct the whole list you have and then reconstruct it with the new thing. Is that the approach I'd want to take for that, or no?
No. And so the first mistake, don't look online.
Okay.
So no, there's an easier approach. So I would look back, and it's kind of like a puzzle, right? So if you look back and look at some of the operations we did already, then you can kind of see maybe how to do the append to back. So we did look at cons, right, which is for appending something to the front.
Yeah.
And then there's kind of this other thing that you can do, which is concatenation, right? So the plus plus. So those are kind of the two main. What?
Sorry to interrupt. Doesn't that need two lists though? If you're just appending.
It does. It does, but there's, you can kind of mess around with that, and you might be able to get that to work.
Okay.
That's a hint.
Thank you.
Okay. But in general, so I think people need to be careful with the homework. I think there's a good thing to bring up is, for the homework, I want you to use the things that we've only touched on in class. So the idea is, the things that we've talked about, I want you to use those things to do the homework assignment, not to go and look, because you can do all kinds of crazy stuff in Haskell, and there's a bunch of ways to do things. So what I want, it's good to go and look for help or ideas, but you need to use the things that we've only talked about so far with respect to the assignments, not like stuff that we haven't talked about. Does that make sense? So the idea is to practice the things we've talked about, not to do things that we haven't. And I don't expect, there's no problem that you have to go outside of what we've already discussed.
Okay, thank you.
Okay. Yeah. And that wasn't directed just at you, but to everybody. And then before we get started, what I'd like, if everybody could just send, just in chat, just put here, just type here. That way I can kind of keep track of who's here. Thank you. Awesome. Okay. Any other questions?
Real quick, do you want a PDF of the HS file included?
No, you don't need to. Just if you just check that in to your GitHub repo, that's good enough. I think Harley will just go off of that. Yeah. But then just one PDF for the write-up, and then the source code file is fine. You don't have to include that. Okay. Any other questions? All right. So this is kind of a little bit of a warm-up. So, and then as part of that, I'm going to talk about a few more functions, and then also some function types. So one function that we didn't get to last time is replicate. So replicate basically takes a number n, and this has to be an integer value, an int value, and then it takes an actual value, and then it returns a list of n values v. Okay, so just as an example, if I say replicate 5 ones, then I'm going to get back a list that has 5, 1, 2, 3, 4, 5, whoops, 5 ones. If people know Python, this is the same as doing, so on lists, multiplication is overloaded for lists. So you can do like the list A or something times 5, and it'll do a list with 5 A's in it. Okay, so it's kind of similar to that. Does anybody know that? Has anyone seen that before? Okay.
It's kind of gross.
Yeah. Okay, so here's my question. Replicate has what type? What is the type of replicate? So first of all, what is replicate? Is it a function? Yes, function. So it's going to have a function type. So the other thing you should be thinking of, well, how many arguments does it have? And what are the types of those arguments?
It has in, where in, or yeah, the type in, where in is an int, and then
Good.
the type v, which could be anything, and then it spits out v in list. So
it spits out what? What's the type? It's a list. What is it a list of?
yeah, so a list.
A, good. List of A. And then, so this would be the first param, this is the second param, that's the return type. But really in Haskell, it doesn't make a difference. And so that the order matters, but the fact that it's a param versus not a param, that's not so important, like we talked about last time. So really you just put an arrow in between these. And what we talked about last time is the way to think about this is replicate takes an int and then it returns a function that goes from A to a list of A. Okay, so But now we're at the point where we know what this means, and we can just say replicate has the type int to a to list of a. Int to a to list of a. And then Ewan asks, is this int or is it integral? I think it's int. I think it is. I'd have to check. Somebody could check for me. Just fire up GHC. And then I think it's an int because most of these functions in Haskell restrict the type to int because, well, how many times are you going to really replicate? Like, how many times do we need to replicate? Excuse me. Okay. So another function that looks like an operator is this index of, basically, and it return. So this takes a list, and it's going to takes a list, and it takes an index. It returns the value at that index. So, as an example, if I have a list 1, 2, 3, 4, 5, and I want the value at index 0, then that's going to be the value 1. Or if I have, again, 1 to 5, I want the third element, that's going to return 3. Excuse me. So in this case, what is the type of the index operator? How many arguments?
Two.
Okay, it has 2. Good. 2 arguments, and then it returns something. What's the first argument? Well, actually, what's the second argument? Any guesses what the second argument is?
A.
No, maybe this is not a great example. So another example would be like if I have I could do a string, so like foo, and I can ask, because it's just a list of characters, so I can ask for the value at index 0. So in this case, it's going to return f, for example. Okay. So again, what's the second argument? So that'd be like the 0, the 2.
Oh, then an int.
Int. Good. So it's int. Okay. And then I think somebody already said this. So it doesn't, excuse me. We don't care. Haskell or the operator doesn't care what the type of list it is, right? It just selects the element at that index. So it's not picky about what the types are. So here it can be a list of anything. Okay. So what's the return type?
A.
So like here it returned a F. Here it returned a number. It's always going to return a number from the list, or a value from the list. So what's the return? What are the values in the list?
A.
What are the type of values in the list? What? A? Correct. Good. Any questions? Okay. All right. So now we're going to look at a function called zip. Zip is like a classic function. Takes a list manipulation function. So basically, zip takes 2 lists, and then it creates a new list of pairs. So it goes through each list index by index, or element by element, pairwise, and it forms a pair out of those 2 elements. So it takes two lists and pairs their elements. That's not very accurate, but it's close enough. So here's an example. So if I say zip 1, 2, and 3, 4, zip is going to return two pairs. So the value 1 and 3, so it takes this one and that one, pairs them, and then it moves on, and it's going to take this value and that value and pair those. You can give lists to zip that aren't the same size, and it just goes up as far as it can. So, for example, if I have the list 1, 2, 3, and I pair that with the list 4, 5, then there's only two elements. I mean, the smallest list has two elements, so it can only do two pairings in this case. So it's going to be 1 and 4, and 2 and 5. The other thing about zip, which is pretty interesting, is that the two lists don't have to be of the same type. So for example, I can do zip of maybe 1, 2, and true, false. Okay, so the first argument is a list of numbers, the second is a list of bools, and the result here is going to be 1 true and 2 false. Okay? Anybody disagree with that? Or think that that's weird? Okay. So, now the question is, what is the type of zip? And again, you should be thinking, well, how many arguments? How many arguments does zip have? Somebody tell me.
2.
2. Okay, so there's 2 arguments, and then there's one thing that gets returned. So what kinds of things are the 2 arguments?
They're both lists.
They're lists. They're both lists. Good. So the first one's going to be a list, and the second one is going to be a list. And what does it return? What kind of a thing does it return?
A list of 2 pair tuples?
Right, a list of pairs, or a list of 2 tuples. Okay, so it's going to be a list of pairs. So now the question is, what kind of goes in? What are the types of the list, or the values in the lists? So I think this example is kind of the most kind of general in the sense that what we can see from the last example of zip we did is that the values can actually be different in the 2 lists. So if we say the first list is a list of A, if we said list of A for the second list, that would be over prescriptive. That's too strong of a constraint, okay? Because in this example, well, we know numbers and Booleans don't match, right? There's no common type. And so that's it's not going to be A there. That's too prescriptive, too strong of a constraint. And so it can be that the 2 lists have different types of values, okay? And so now what does that tell us about the output? What's the output type now? We know it's a list of pairs, but what are the types of each element of the pair?
A and B.
A and B. Good. Excellent. So that's the type of zip. So zip gets its name, it's like a zipper, right? Like you're kind of combining the 2 lists together in that way.
Do you ever use key value pairs in Haskell?
So there are kind of like, yes, but also actually something like just two tuple can act as a key value pair.
Yeah, so could you zip like a list of keys with a list of values?
Yeah, that's right. Yeah, that's good. This is the most, like a list of two tuples. That's the most straightforward way to implement a key value pair collection or something. Yeah. Okay. So the next one that I'm gonna just go over again or talk about is, I don't think we've done it yet, is elem or element. So elem X, and then takes a list. And basically, elem just checks if X is an element of the list. Okay, so it returns true if X is in the list. So just as an example, I want to know, is 1 in the list 4, 1, 5, 3? Yay or nay? What's this going to return?
True.
True. And then what about if I asked if 0 was in that same list? What's that going to return?
False.
False. Good. Okay, what if I wanted to know if A is in the list 4, 1, 5, 3? Well, let's hold off on that. Let's hold off on that for a sec. Okay, let's first look at what the type is. Again, how many, elem takes 2 parameters, okay? So we're gonna have something like this. What's the type of that, what is the return type for elem?
Boolean.
It's a bool, good. Okay, and then the second argument's a list, and the first one is a value. And so in order for this to work, somehow we're gonna have to like iterate through the list, right? We know this from 223 or 122 or whatever. The way I check if this value is in the list, or if I come up here, this value is in the list, is I have to go one element at a time, and I want to do a comparison. I want to know, is 1 equal to 4? If it is, then I return true. Otherwise, I keep going, so then I get to the second element. Is 1 equal to 1? Yes. Okay? So that's kind of how the algorithm would work. We all know this. So that means in order to implement elem, I have to use equal, right? I have to do a comparison of the value and the 2 values in the list and the value that I give. In order to do this comparison, so the type of this, whoa, what did I do? Sorry. The type of equal requires that the 2 operands are of the same type. The 2 operands for equal have to be the same type. They also have to implement EQ, right? The EQ type class. And so what does this tell us about the type here?
They're the same.
They have to be the same. Otherwise, we can't use equal. So we'll call that A. And again, elem is going to use equal to do the comparison, or not equal, doesn't matter. Could use either one of those. And what we know is that those, in order to even call those, the operands have to implement the EQ type class, because these are both defined in EQ. Okay, so what this means is that not only do they have to have the same type, but that type has to be part of the EQ type class. Okay, so that would be the type of elem. So if I come back over here to this example, what's going to happen when I try to ask, is A in that list? So there's some choices. It might say true, it might say false, or I might get some kind of an error. What do you think is going to happen?
Error.
Somebody take a guess. Error, okay? And in particular, this is going to result in a type error. It's not a runtime error, it's a type error. And the reason is because char and a number are incompatible types. They're incompatible, and so this call is not going to type check at all, right? It just doesn't even pass the type checker. Are there any questions about that? Okay. All right, so now, I think the last one, there's a couple here. Two more. Yes, two more here. So the next function, I just want to show you, we'll talk more about these kind of in a second with respect to the types, but I just want to show an example here real quick. So, and it's an example of a higher order function. And then I just want to say that oftentimes I'll abbreviate, or people abbreviate higher order function as HOF. So HOF instead of writing higher order function all the time. So the higher order function we're going to look at is a function called filter. And the basic idea is filter is going to remove element. It's going to have, it appears to be removing elements in a list based on a predicate function. And what I mean by predicate is it returns true or false. It's a Boolean function. Somebody. There we go. Okay. So the first thing, so basically the idea is filter takes two things. So the first thing it takes is a function, this predicate function, and then the second thing it takes is a list. Okay. So just as an example, I'm going to, the predicate function I'm going to give to filter in our example is the even function. So even basically takes a number, so like 2, number 2, and then it returns true or false depending on whether or not that number is even or not. So in this case, it's going to return true because 2 is even, whereas like even of 3 would be false. Okay, so then if I want to know what the type of even is, kind of at its core, it takes a value and then it returns true or false. And so this is kind of the notion of a predicate function. A predicate takes a value and returns true or false. Okay, in this case for even, it turns out that even only works for certain types, which are the integral types. So like int, integer. Okay, so there's this type constraint. But the core of it is it takes a value and it returns true or false. Okay, so then filter, an example of using filter is I can call filter, and then I'm going to pass in the even function, and then I give it some values. So here, the list is going to have the values 1 through 10, and the basic idea of filter is it goes element by element, again, through the list. So we go element by element, and for each element, it basically takes that value and it plugs it into the even function if this value plugged into even returns true, then the value gets put into the output list. Okay, so in this case, 1 is not even, so it's not going to go in the output. Whereas the next value, 2, is even, so even of 2 is true, and so then 2 goes in the output list. 3 is not even, but 4 is, so is 6, so is 8, and so is 10. So that the result is 2, 4, 6, 8, 10. All the even numbers in the list. Okay. So one of the cool things about Haskell with the lazy evaluation is I can do something like filter, even, and then an infinite list, like 1 and on, and I can store that result in I can bind that function call basically to something, and then I can start asking for like what's the first even number, what's the 100th even number, etc. So there's some kind of cool stuff you can do with this. So the reason I bring this up now is in a second we're going to talk about higher order functions, and it's kind of the last thing we need to understand when we're talking about function types, because filter is different with respect to its type because it takes a function as an argument, because it's a higher order function. So we're going to come back to this in a second. Before we do that, for the next homework assignment, I need to tell you about a function that you're going to use, which is the error function, or that you'll. I think I'm asking you to use this. So basically, the idea of error is that it throws an exception. So when you call error, you pass it a string, which is the message, and then it aborts execution, and it basically just stops the function and throws an error. And we've already seen some examples where we throw exceptions. For example, error is used if I ask for the tail of the empty list, right? So that there is no tail of an empty list, and so this results in an exception. And the way that that's done is by calling the error function. Okay, so let me give an example. So let's say I want to define a function called second_elem that takes a list, and basically it's going to return the second element of the list. Okay, so it's a kind of silly function. So I'm going to implement this by kind of different cases. So if the length of the list is greater than or equal to 2, then there's a second element, right? So in this case, if the list is big enough, then I'm going to return the head of the tail. Okay, that's the second element. Otherwise, I got a problem. There's not enough elements to return the second element. So here I would use the error function and say something like list too short. Okay, so then given that, if I call the second elem function on the list 1, 2, right, it's going to return 2. Okay, whereas if I call second elem on a list with the value 1, I hit the error case. And so what's going to happen is it's going to print out this exception, and then it prints my message, list too short. Okay, any questions about that? It's pretty simple. Okay, so now I have a question for you. What is the type of error? What on earth is this function's type? Because it's just a function like any other function. It's not a special anything in Haskell. Well, it kind of is, but it's not. a function like any other function. So it has a type. So how many arguments does it take?
One.
Takes one. Okay. And what is it? What type is that argument?
List of chars.
Exactly. So it's a string, or in other words, a list of char. Okay, so now here comes the tricky part. What is the return type? Well, in some sense, like, it doesn't really return anything, right? Because it throws an exception. However, the type checker doesn't know this, right? It just looks at it as another function call. So when Haskell comes in and wants to type check this function, make sure this function has the right type, then it needs to fit error into that calculation. It needs for error not to be a special case. It has to fit in with all the other cases. And so the way Haskell does this, or the way to get this to work, is error has the type list of char to any type, which means basically whatever type the function's returning, kind of like in the normal case, so like here, error just kind of morphs itself to that type. Okay, it's kind of cool, actually. So this is basically the declared type for error. Okay. Any questions about that? Okay. So we're going to keep talking about higher order functions again, and in particular their types. So I'm going to do another higher order function, which is any. Okay, and again, any takes a predicate. So in this case, I'm going to pass in the even predicate, and then you give it a list. So in this case, I'm going to give it, whoops, this list. And any, instead of returning a new list like filter, so it does something similar, but it returns true or false. So it returns a Boolean, and it's going to return true in this case if any of the values in the list satisfy the predicate. So if any of the values in this list are even, then any is going to return true. What is any going to return in this case?
False.
False. Okay. This is a list of odd values. Whereas if I were to say any odd in the same list, in that case it would return true. And you can think of it, it's like a short circuit basically. So it takes the first value, passes it into the odd function. If odd returns true, then we're done. If it returns false, then I got to move on to the next value. And I do that until I don't have any values left. Okay. Any is kind of nice because it actually has a pretty simple type for a higher order function. Okay, so in this particular case, so any really actually has two arguments. So it has the function, because any is a higher order function, the first argument in this case is a function. Okay, so the first argument is a function, and then the second argument is a list. Okay, so it takes two arguments. So function, and then a list of values, and then it returns either true or false. And then, so what we said earlier is the type of a predicate is going to be some value to bool. So that's the notion of a predicate. It's a Boolean function. It takes a value, returns true or false. Even has like an additional type constraint on A, which is that it has to be an integral. Okay, but that's only for even. You can have other predicates that don't have any type constraints, let's say. They're not very interesting, but you could have that. So from any's perspective, it just takes this generic predicate function as the first argument. Okay, so if I were to just write this here, the predicate function, so a to bool, to list of a, to list of bool, or to bool, then you might think I'm capturing this notion of the any type. But it turns out that this is actually saying something different. This expression is really describing a function, the any function, as taking 1, 2, 3 inputs and producing an output. But that's not what any does. Any takes 2 arguments. It takes a function, and then it takes a list of values. And so so when you're doing higher order functions or looking at higher order functions and their types in Haskell, there has to be a way, or Haskell provides a way to specify that this thing, which is looks like just more arguments, is actually expecting a function, not just arguments. And the way you do that is you just put the function in parentheses. So what this is specifying is that this is a function as opposed to just another, like 2 additional arguments. And it doesn't really make sense in this case, since what's getting returned, this is getting returned. I wouldn't call any with the value 1 and true or something like that, right? This doesn't make sense. So instead, you have to explicitly tell Haskell that the first argument in this case is a function, and you do that by wrapping it in parentheses. Okay. Any questions about that? So if you're looking at a function type and you see parentheses in the function type expression, okay, the syntax, then that tells you that what's in parentheses is actually expecting a function there. All right, so I'm going to give you a few more examples here real quick of higher order functions. So the first one, and we'll talk more about these later, it's just to give you kind of a sense for what these are. So the first one is the map function, which is like the most famous higher order function ever. And the basic idea of map is it applies a function that you pass in to the elements of a list. Okay, so as an example, if I have the list 1, 2, 3, 4, and I want to apply the even function to the list, what map does is it takes the first element and it plugs it into even, and what it gets back from that call, it's going to put in a new list. So even of 1 is false. Even of 2 is true. Even of 3 is false. And then even of 4 is true. Okay, so here's another example. Let's say I have a list, 1, 2, 3, 4. And I want to add 1 to all the elements of the list. So I can do that by using a partial function. In this case, I'm going to add, I'm going to pass in +1. And so what this is going to do is it's going to go 1 by 1 through the list. It's going to take the value. It's going to plug it into the +1 function. Okay, if you remember, I can say plus like 1, 1, for example, or I can say plus 1, 2. So 1 comes in as the second operand of the +1 function, and so it's going to put it's going to calculate that value and put it in a new list. So here it's going to, the first element's going to be 2. Then it's going to take 2 and plug it into the +1 function. That's going to give me 3, and then 4, and then 5. Okay. There's tons of stuff you can do with, yeah? Is there a question?
So with the +1, would you have to put parentheses around the plus for it to be a function, or?
Not in this case. It's enough to just put parentheses like this. This is all you'd have to do. You could put parentheses around the plus, but you don't have to in this case.
All right.
So what I'd like to say, map is like one of the coolest. There's cooler higher order functions, but map is like one of the coolest ones, I think. And what I usually like to say is that basically this map function, not the one in Haskell, but just in general, this idea of map, where you have a list of stuff and you apply a function over that list, that's how Google made all of their money. So if it wasn't for the map function, we would not have Google today, or Google would never have existed. Okay, anyway. So the real question is, what is the type of map? That's the question. Okay, so the first thing to figure out, just like before, is how many arguments does it have? How many arguments does map have? 1, 2, 3. What do you think?
2.
2. Good. And it turns out the first one is actually a function. So we're going to put that in parentheses first. Okay. And then we can see the second argument is a list. And we'll just say that's a list of A. Okay. And we can see what gets returned as a list. If I look back up here, I can see that the list 1, 2, 3, 4 and the output list can be of completely different types. Okay, so what that tells me is that if the input is a list of A, the output can be like a list of B. They don't have to be the same type. Okay, what I know is that so all I have left is this function that gets passed. So with respect to the function, I know it takes an A, it does whatever it needs to do, and then it outputs a B, right? Because it goes element by element through the list. Each element gets plugged into the function. What gets returned gets put into the output list. Okay, so what does the type have to be here of the function that gets passed into map? So what does this type have to be? Given that A to B. Good. Okay, so that's the type of map. So it takes a function that maps A's to B's, and then it takes a list of A, and it returns a list of B. One of the coolest things about Haskell, and it takes a while to kind of get used to this, is that the type of the function, so the type here, actually tells us everything we need to know, for the most part, about what the function does. It's depending on the type. In this case, for map, because it's so generic, it has no type constraints, it's just this very generic type, we can actually deduce what map does, or pretty close to it. There's only a couple things map could possibly do here. Okay, so the next one that I want to talk about, and then we'll move on to talk about recursion. So we can start defining these functions on our own without just relying on them existing. So the last higher order function I want to talk about is zip width. So we already talked about zip, which takes two lists and pairs them up. So zip width is very similar. It takes two lists and a function. It the way you can think about it is it basically zips the two lists together, and then it maps the function over the pairs. It doesn't quite work that way, but that's the basic idea. So it applies, sorry, bad handwriting. It applies a given function to each zip pair. It's not really the way it's implemented, but that's the basic idea of it. Okay, so I'll give you an example, a very simple example. So here I have zip width. The function is plus, okay, and then I give it the list 1, 2, 3, and the list 10, 20, 30. So what zip width is going to do is it's going to take the value 1 and the value 10 and plug those. This will be the first argument, this will be the second argument into the plus function. And then it'll output the result. So here it'll be 11, because 1 plus 10 is 11. And then it'll take the second argument, so 2, or the second element of the list, so it'll be 2 plus 20, so that's 22. And then 3 plus 30, that's 33. Okay. Another example would be if I did less than. Okay, so 1, say 1 to 40, and 10, 20, 30. So again, it'll do these pairwise comparisons, and it's using less than. So it'll be 1 less than 10, which is true. It'll be 2 less than 20, that's true. And then 40 less than 30, that's false. Okay. So now the question is, what is the type of zip width? So this will be the most complicated one function type we've seen yet. So how many parameters does zip width have?
3.
3. Okay, so and the first one we know is a function.
3.
Good. Okay, so then the first one's a function. The second two are lists. And then what does it return?
List.
A list. I didn't give an example of this, although we could come up with examples. But I'll just tell you what the sort of the general type is. So it turns out, and we can kind of see this here. So the input lists can be different than the output list, and also depending on what this function is, the two input lists can also be different, right? So if I had like a list of lists here, and then I had indexes here, and I use the index operator, that's going to create a, so this list would be different than this list, which would be different. Well, then this would not be different, okay, but whatever. The most general form of zip width is that this list, and this list can all have a different type. And then the zip width function takes 2 operands and returns a result. And so the first operand has to be of type A, the second B, and then it returns a value of type C. So that's the full type of zip width. So again, higher order function, the other 2 parameters, and the return type. So once we get through kind of recursion and pattern matching, we'll come back to these higher order functions, and I'll show you kind of how to define them. And in particular, there's one in particular higher order function that is the mother of all higher order functions. So basically you can define any other higher order function using that higher order function. So, and I'll talk about what's some cool things about higher order functions and why it's generally good to use them when you're doing programming. However, for the homework assignments for now, I'm not expecting you to use them. I just wanted to show you this to kind of wrap up talking about function types and then some of the kind of cool things you can do fairly easily with just these higher order functions. All right, so now we're going to move on to recursion. And so I'm just going to give some examples of how to use recursion in Haskell. It's really simple. So the first example I'm going to do is sum the list, the elements of a list. And again, when we think about recursion, we have to, we generally think of it like an inductive definition or where you have like a base case and then you have a recursive step. There's always a base case, otherwise you loop forever, and then a recursive step or steps. So to sum the list, what's the base case? If I have a list of values and I just want to add them all up and return their sum, what's the base case?
One and no elements.
Say it again.
0 elements. Would that be it?
So an empty list?
Yeah.
Yeah. So the sum of an empty list would be what?
0.
0. Good. Okay. And then the recursive step would be basically first we take the first element because we know it's not empty, right? Plus the sum of the rest. Everything minus the first element. That would be the recursive step. So basically, our leap of faith is that we can sum up a list. So if we can sum up a list, then we can easily just take the first element, get the sum of everything else, add that together, and now we've got our sum. Okay, so I'm going to basically show you how this works. So, or give one definition of this using recursion. And there's really nothing special you have to do. Super easy. So I'm going to call it my sum, and it's going to take a list of values, x's. And so then I have to do the base case. So if this list is empty, and one way to do that is to use this null function. So null returns true if the list is empty. Okay, so if the list is empty, then, or null, then I return 0. That's my base case. Otherwise, I'm going to take the head of the list and I'm going to add it to the result of calling my sum on the tail of x's. Okay. So sometimes I'll ask you, are there any questions about that, actually, before I keep going? That's all we have to do to define this. Super easy. So sometimes I'll ask you to kind of show the evaluation of a function. And so I'm just going to walk through that. So here's like the evaluation steps. It's a lot like derivation in grammars. If you think way back, which seems like last year or something, when we're talking about grammars and derivations, that was forever ago. So the way you show an evaluation is basically kind of like what you would do with a derivation. So if I call my sum on the list 2, 4, 6, then the way that this works is, and what Haskell's doing is it basically takes this my sum of 2, 4, 6, and it's going to replace it with what's on the right-hand side of the equals. Okay, it's going to replace it with the right-hand side of the equals. So in this case, we can kind of skip a step, which is the if null of x's, then 0 else head of x's plus my sum of etc. But really, one step evaluation of my sum is just to return the right-hand side. Okay. In this case, we can kind of skip that step since we can kind of evaluate on the fly the if then else. Okay. So here, well, maybe I'll just do it the first time anyway. So I'll write it out as an if then else. So it would be if. So if I replace my sum of 2, 4, 6 with the right hand side, I would say if null of 2, 4, 6. Okay, then 0 else. Head of x's plus my sum of the tail of x's. Okay, so that's one step. So now if we do another step, basically we take this and we're going to evaluate the if then else. So in this case, since that is false, then we're going to replace this whole thing with that. So we have head of, actually what goes here is 2, 4, 6, and what goes there is also 2, 4, 6. Okay, so I ran in a room. So then I'm going to take the head of 2, 4, 6. I'm going to add it to the result I'm calling my sum on the tail of 2, 4, 6. Okay, so if I keep going, the head of 2, 4, 6 is just 2 plus my sum of the tail of 2, 4, 6. So this is going to be 2 plus my sum of 4, 6. And actually, we don't need the parentheses anymore. So then I have 2 plus, and now I would just replace that with the right-hand side of my sum again. So it'd be another if, etc. And we just basically keep going, building up. The right-hand side by we just keep taking the head, and it's going to end up being 2 plus 4 plus 6. Eventually, we'll get to an empty list, and so then it'll be plus 0. And that's essentially the result of all of this. Okay. The other thing that's pretty cool in this case is that if I give, let me just copy this. If I come back to the definition, if I ask Haskell, what is the type of my sum? Okay, so it is going to look at the right-hand side, and from what's given here, it's going to deduce or reason over the expression to come up with the type of my sum. Okay, so how does this work? Well, it basically, first of all, it knows what the input is, right? This x's thing. So it knows it has one input and it produces one output. And you can just look at the function to see that in this case. Then it's going to try to figure out what is the input type. So here it can see we're calling null on x's. So it turns out that null has the type list of A to bool, right? And so that tells us that the input type has, because we're doing this over x's, has to be list of A. And then we can do the same thing here. So and this is almost like a type check. So head takes a list, the head function takes a list of A and returns an A. Okay, so then this is almost like a type check. What is X's? And I'm passing that into this head function. It better kind of be of the right type. So, well, it is. It's a list. So we're good there. And then we're going to take that and we're going to add it to another call of MySum, right? And so we do know something about plus. So the plus function takes two values and then returns a value. In addition, it has to be such that A, in this case, the type, has to be a number. Okay. In other words, plus is actually defined as part of the num type class. And so since we're doing plus in the else case, this tells us that this thing has to result in a number type, okay, and that this thing, the second operand of the plus, also has to be of a number type, and those have to be the same. And so from this, it can deduce that the result is going to be an A, because the result of num A to A when we're doing plus is A. Okay, and then it also can deduce that what has to be inside of the x's is a number. Okay, so it'll figure out that my sum has this type. List of beta A such that A is a number type. That's pretty cool, that it can go through kind of this reasoning process and figure this out. Okay. I'm gonna go through, we don't have a lot of time left. I'll go through another couple examples. Hopefully we'll have time. So the one I want to do next is the drop function. So we would write like drop some number of values in a list, x's. Okay, so for example, drop 2 from the string foobar is going to drop the first 2 elements of the list and return the rest. So this is going to return O bar. If I similarly, if I drop 4 elements from foobar, then I'm going to drop the first 4, so this will return AR. I can pass in different types. So for example, if I drop 4 elements from the list 1, 2, then I'm dropping the first 2, and then there's no more elements to drop. So in this case, it's just going to return the empty list. I can also drop 0 elements from a list. In this case, that just returns the list. Similarly, I can drop like a negative number of elements. Again, there's nothing to drop, so it's just going to return the list. Okay. All right. So given this, if we're going to try to define the drop function, okay, what are the base cases? I guess another example is I can try to drop any number of elements from an empty list. I'm always going to get back to the empty list. Okay. Any guesses as to what one base case might be?
Less than 0. Less than or equal to 0.
So if n is less than or equal to 0, okay, then what do we do?
Return the list.
Return the list. So there's nothing to drop. We just return the list. Is there another base case? There is. What is it?
When n is equal to the length of the list.
Not. That could be, but no. Okay, this is an art. Yeah. Sorry, what?
When the length of the remaining list is 0. When the list is now.
Okay. So an empty list. Again, in this case, there's nothing to drop. If n is equal to the length of the list or bigger, that could also be a base case. In that case, again, there's nothing to drop. Okay, but the way I'm going to define it using recursion, we don't really need that case. It's handled by the other cases. Okay, so let me just give you an example. So the basic idea is I'm going to go, so in Haskell, you can't modify a given list, right? So you're always creating a new list. And so that's a little bit the basis for why we're doing these base cases. So what we're going to do is, as long as we're not in a base case, we're going to essentially just kind of advance through the list. If there's something that needs to be dropped, we're in a case where we need to drop something, we're just not going to include that value in the output. So as we're going to iterate through the list, and as we iterate through the list, we're basically choosing to drop things or not drop things. So in the main case, there's still things to drop, and so we just don't include that stuff in the output. Whereas when we get to a base case, there's nothing left to drop, so we just return the list as it is. Hopefully that makes sense. So the way we're going to define this is using, again, a conditional. So if n is less than or equal to 0, that's a base case, or if x is empty, those are the two base cases, then we're just going to return x's. Okay. Otherwise, we're going to recursively call myDrop, and we're going to drop. We're not going to include the first element in the list. So in this particular case, we included all the elements in the list. For the second case, we're not going to include the first element, and the way we do that is by recursively calling myDrop with a smaller n value and shrinking the list. So we're going to take the tail of the list. So we're basically not including that first element in the recursive call to myDrop. So if I was going to write this out as a derivation or as an evaluation, I might say, like, I want to drop one element from the list 10, 20. Okay, so on the first pass, if I look at the conditions, so n is not less than or equal to 0, and the list is not null, and so I'm going to replace this left-hand side with this right-hand side. So I'm going to do myDrop of 0, which is n minus 1, and then the tail of 10, 20, which is the list 20. Okay, then on the next call, I'm going to replace myDrop 0 of 20 with the right-hand side. So since n is 0, this first condition passes, and so I just return 20. All right, so actually this is a good example. You might want to try this on your own, where there's all these cases, like when n is bigger than the list, or it's the length of the list to drop, or it's less than, it's 0 starting out, or it's less than 0, or whatever, just to see how the different cases fit in with this. But I think for the most part, it's very straightforward. And we're out of time. And so we'll pick up again on Thursday. We'll finish up with recursion. Actually, at this point, you have everything you need for the recursive part. You're also basically in a position where on Thursday, when I post the homework, the next homework, you can do half of the homework assignment at this point. But we'll talk on Thursday about the second half. So I'll stick around for a few minutes if people have any questions. Otherwise, I'll see everybody on Thursday.
Thanks, Professor.
Yeah, thank you.